Logarithms have many uses in science and engineering. We'll see what the relationship is between logs and indices. We'll use the index laws to help us develop the log laws, which can be used to help simplify logarithmic expressions. And we'll see how we can solve some simple logarithm equations. Logarithms have many applications, as can be seen from this long list of fields where they are used. Let's revisit our paper folding activity. We had a sheet of paper that we folded over several times and we counted the number of layers. So if we have no folds, we have one layer. One fold, we have two layers. Two folds, we're doubling that number of layers to 4, and we're doubling as we go down that list. So that's an exponential relationship, 2 to the power of n. If we know the number of folds, we do 2 to the power of the number of folds to get the number of layers. So that is an exponential relationship. If we go backwards and work out the number of folds from the number of layers, then we take the logarithm. So the logarithm of 8 is 3. This is a graph of our exponential relationship. So we read off the number of layers on the y scale from the number of folds. For example, if we have 3 folds, we read off that we have 8 layers. Now, going backwards from the number of layers, if we read off the number of folds, we are taking the logarithm. The logarithm is just the inverse of the exponential function. The exponential equation 5 to the power of 3 equals 125 can be rewritten as a log equation, as log to the base 5 of 125 equals 3. Those two expressions state the same thing. So the relationship between the two is that the 5 is the base, the 3 is the index, and the 125 is the number. So notice that when we are finding the log of a number, we're really looking for the index, the 3 in this case. Let's find the inverse of the exponential function y equals b to the power of x, where b is some number. Now to find the inverse, we need to interchange the y and the x in our original function. So there it is there. And now we can rewrite that as an equivalent log statement, that is log base b of this number x is the index y. That is y equals log base b of x. That last expression there is the inverse function of the exponential function. So we can see that b to the power of x and log base b of x are inverse functions. They will undo one another. So if we have log base b of b to the power of x, the log base b will undo the b to the power of, and so we end up with x. Or if we do it the other way round, we'll have b to the power of log base b of x is also equal to x. These two are examples of functions of functions. And when the function of a function is x itself, then we have inverse functions. Because the exponential and log functions are inverses of one another, their graphs will be mirror images of each other about the line y equals x. In this example, we're asked to rewrite this log equation as an index equation. So we need to identify the base, which is 3. The logarithm is the index, that's the 4. And the number there is 81. So we'll rewrite that now as the base 3 to the power of 4, the logarithm or index, is equal to 81. Here we're asked to evaluate log base 6 of 1296. So what we're really being asked here is to work out what the index is when we write 1296 as 6 to some power. So 1296 is 6 by 6 by 6 by 6, which is 6 to the power of 4. So our logarithm is going to be that index 4. So the log base 6 of 6 to the power of 4 there is the index. The answer is 4. The log is just the index. Let's use the index laws to develop the log laws, which will help us to simplify log expressions. If we have m lots of b and n lots of b, we saw in the last video that we add the number of b's together. And so if we rewrite the b to the m as an x and the b to the n as a y, then on the left hand side there we have x times y, and on the right hand side of course we've still got b to the power of m plus n. Now we can rewrite that expression as a log expression there. So the log now of the left hand side there, x times y, is the index. So that's the m plus the n. And the m, of course, is the log of the x, and the n is the log of the y. So we can see that when we're multiplying those two numbers, x times y, that what we're really doing is adding those indices, adding the logs. Same thing happens when we're dividing. Again, using x and y as above, then what we have on the left-hand side is x divided by y. And again, if we take the log there, the log of this left-hand side, of course, is the index. And the index there is m minus n. And so we're subtracting the logarithms. The m, of course, is the log of the x, and the n is the log of the y. And lastly, when we have b to the power of m raised to the power of n, then once again replacing the b to the power of m as an x, then what we have on the right hand side is b to the power of m times n. And so now looking at the log of that, then the log of the x to the power of n is the log of x, which is the m, that we then multiply by the n, because of course the log is the index. Let's have a look at some examples where we can use the log laws to simplify some expressions. Here we have the sum of two logs to the same base. So that means that the numbers are being multiplied. We had in the previous slide that the log base 4 of 3 times x is the log base 4 of 3 plus the log base 4 of x. In this more complicated example, we have the 2 out in front and we're subtracting. So firstly, we need to deal with this 2 here. We're multiplying this log by the 2. So therefore, we can rewrite that as log base 2 of x squared. That 2 can come out there in front of the log, 2 times log base 2 of x. And now we've got two logs that we're subtracting, same base 2 in this case, and so that means we can divide those two numbers. There are two bases that are used most often. The first one is base 10, that was traditionally used in doing calculations because our numbers are based on 10. So log base 10 of 10 is 1. That's the power, of course, 10 to the power of 1. Log base 10 of 100 is 2. That's 10 squared. 10 cubed, the log there is 3. So they're nice and easy to calculate. And because they were used a lot, they were called common logarithms, and we didn't bother writing the base 10 there. So it's just written as log of x without a base. It's understood that the base there is 10. However, in some textbooks, you might see that log x actually refers to a log base e, which we'll have a look at next. Now, e is the easiest base to work with in mathematics, for example, for differentiating, so we tend to use that base more often in maths. And it's just written as log base e, or natural log, abbreviated to ln. So natural log of x really means the log base e of x. Let's look at some examples of how we can calculate these logs. Now, as we saw before, our log without a base means log base 10. Here we have 10 to the power of 4, so the log is the index. The log base 10 and 10 to the power of course, are inverses, so we end up with just that 4. Log, again base 10 of 0.0001, is log base 10 of 10 to the negative 4, so our log there is negative 4. Let's have a look at a natural log now. Log base e of e, or natural log of e, is just the power once again, that's e to the power of 1, so the log there is 1. And log of 1, well, 1 is e to the power of 0, and so our log there is 0. An application of logarithms is the pH scale that's used in chemistry and medicine to measure acidity. The acidity depends on the concentration of hydrogen ions in a solution. pH is defined as the negative log base 10 of the concentration of hydrogen ions in a solution, which is measured in moles per litre. In this example, we're asked for the pH of a solution given its concentration. So we start off with the definition of pH, and then we substitute the known value for the concentration of hydrogen ions, and then we evaluate that on a calculator. In this example, we're given the pH as 2.6 and we need to find the concentration of hydrogen ions in the solution. So once again, we start off with the definition of pH and we put in the value of 2.6 in for pH. We can then take the negative of both sides, and then to undo the log function, we have to do the inverse function, which is 10 to the power of. Or we can think of rewriting this log function as an exponential. The base is 10, the power is negative 2.6, and the number is the concentration of hydrogen ions. We can calculate that out on our calculator to get our answer in moles per litre. Sound intensity measured in decibels provides another application of the log scale. Humans can't detect the difference between sound intensities very readily, so a log scale is used. The perceived sound is given by this formula here, where the I is the actual physical intensity of the sound, and I naught is the intensity of a barely audible sound. In this example, we need to find the sound intensity in decibels when the sound is 100 times that is barely audible, I naught. So we use the formula for sound intensity. We substitute I equals 100 times I naught into that formula. We can cancel down our I naughts there inside the log, so we'll get 10 log of 100. Now, log without a base written means log base 10, so log base 10 of 100 is 2. 2 times the 10 is 20. So the perceived loudness here is 20 decibels. So we've seen how exponential and logarithm functions are inverses of one another. We've derived the log laws from the index laws, and that helps us simplify our log equations. And we have seen how we can go about solving log equations. And we've looked at an application or two of logarithms.